Charges on a number line. Our first problem will be two charges on a number line. We have two negative charges, minus 24 microcoulombs at negative 6 meters away from the origin, and another charge, minus 18 microcoulombs at 4 meters away. Find the magnitude and direction of the electric force between the charges. Find the magnitude and direction of the electric field at the origin. Right here, we want the field there. And notice, the field is not, there's no charge sitting there. It's all by itself. It's empty space. C, find the magnitude and direction of the electric field at the origin due to charge Q2. And then find the net electric field due to both charges. And where? At the origin. Then find the electric potential at the origin. Notice there's no charge there, you're just in free space. Due to charge Q1, then find the electric potential at the origin due to charge Q2, find the total or the net electric potential at the origin, and finally, how much work must be done by an outside force to bring a 10 nanocoulomb test charge from infinity, put infinity out here, to the origin. Find the magnitude and the direction of the electric force between the charges. Both charges are negative, so they'll repel each other. So the direction is repelling or away from each other. Don't get tricked and say that the force is to the left or the right, because one force goes in each direction, right? Here's the force on object 1. Here's the force on object 2. So left or right is meaningless here. You want to say repelling or away from each other. To find the magnitude, well, we know we have an action-reaction pair here. The force of 1 on 2 is equal to the force on 2 of 1. Of course, that's the magnitude. So that's going to be kq1 q2 over r squared. We find the distance between them. Well, one's at negative 6 on a number line, the other's at 4. So that distance is 10. We plug in k. We plug in our charges. Now, what do we have to do with the charge? They're microcoulombs, so we have to turn it into coulombs by multiplying by 10 to the minus 6. Divide by the distance squared, make sure you square it, and the magnitude of the force between these two charges is 0.0389 newtons. Okay, now let's find the electric field at the origin. A handy thing to do is to mark where we're finding the electric field. Right there. Okay, right at the origin. Notice there's no charge there. You're just in space. You want to find the field. The electric field is always in the direction that a positive test charge will move. So let's imagine a positive charge located at the origin. Q1 is negatively charged, so it would attract the positive charge. The direction to the left, because the positive charge would want to move to the left due to Q1. So we're going to ignore Q2 for now. We're just worrying about what Q1 is going to do. Okay, so we know the electric field due to Q1 at this point here is going to be to the left, right? A positive charge will move towards a negative charge. We have our equation for the electric field. We're just going to work with the magnitude. So we have K. We convert the charge to coulombs by multiplying it by 10 to the minus 6. And what distance do we use now? We use a distance of 6 meters because the origin is 6 meters away from Q1. Plug our numbers in, and we get a magnitude is 6,000 newtons per coulomb. No negatives in this equation. You just want the magnitude. And we already said the direction, it's to the left. So the electric field at the origin, due to charge 1, we're calling it E1, is 6,000 newtons per coulomb to the left. Find the magnitude and direction of the electric field at the origin due to charge Q2. So again, we imagine a positive charge at the origin. And this time, don't worry about Q1. We already took care of that. Q2 is negatively charged, so it would attract the positive charge. So E2 will be to the right, pointing towards Q2. A negative charge can make electric fields to the right and left, depending on where you are in the number line. So let's look here. Let's just put another, what's the field over here due to the negative charge? Well, it would point this way. It would be to the left. But over here, where the origin is, the electric field is to the right. Now let's find the magnitude of E2, the electric field due to charge 2. It's just kq2 over r squared. The distance now is 4, so we have 4 meters squared in the denominator. We convert the microcoulombs to coulombs by multiplying by 10 to the minus 6th, and we get the magnitude of the E field is 10,125 newtons per coulomb. Don't put any negatives there. This is a magnitude. We're finding the direction by looking at our diagram up there. Now we want to find the magnitude and direction of the net electric field at the origin due to both charges. Now we bring in both electric fields. This is called principle of superposition. We have E1 going to the left and E2 going to the right. We need to do a vector sum. So E2, since it's pointing to the right, will have what? A positive sign. E1 will have a negative sign because it's going to the left. So the sum of the electric fields, here's our E2, it's positive 10,125 newtons per coulomb. And E1 is going to be negative. It's a negative 6,000. See, we're getting all the signs right off this picture here. And then we deal with the magnitudes calculated by the definition of electric field. Add them together, you get 4,125 newtons per coulomb. That's positive, so the net electric field is to the right. Don't worry about getting the sizes of these arrows correct. Don't need it. We're going to see the numbers when we do the calculation, but make sure you get the directions correct. Now we need to find the electric potential at the origin due to charge Q1, and then Q2, and then net potential. This is a lot easier. We don't have vectors here, so we just need our equation for the voltage and the distance. So Q1, well, it's still 6 meters away. And this time you have to use negative or positive, all right? Because there's no vectors here, but we're allowed to use a negative voltage and a positive voltage and add them together. So this is in bold, so you know this is important. Use the sign of the charge. Also, convert microcoulombs to coulombs, and since it's negative, there's my negative. And we will have a negative voltage due to charge 1. We don't have a direction here. This doesn't tell you the direction of voltage. There is no direction. It just lets you know where on the number line it is, whether it's a negative voltage or a positive voltage. Now let's find the electric potential at the origin, marked here with an X, right? We don't care whether there's a positive charge, a negative charge, or nothing. We just want to find the scalar potential. We have our equation here, kq2 over r. The origin is 4 meters away from the charge, so r is equal to 4. We have K, Coulomb's constant. Here's our charge. We convert microcoulombs to coulombs with the 10 to the minus 6. And we put the negative in. It's a negative charge. Divide by 4 meters. It's not squared, right? This isn't a force or a field where you square R. Here it's just all by itself. We get a voltage of negative 40,500 volts. The net electric potential due to both charges at the origin, we just add them together. Okay, just sum the voltages up. You don't have to worry about direction. Voltage is not a vector. However, you do have to worry whether it's negative or positive. That's not telling you direction. It's just where the charge would exist on the number line, whether it's a negative charge or a positive charge. In this case, they're both negative, right? Because they're both negative charges. Add them together. We get the voltage right here at the origin is negative 76,500 volts. Finally, for this particular question, how much work must be done by an outside force to bring a 10 nanocoulomb test charge from infinity to the origin? We just calculated the voltage at the origin to be this negative 76,500. So if we consider a location farther from Q1 and Q2 than the origin, the voltage would be closer to 0. If the location were moved infinitely far away, then we can say that the voltage is 0 at that location. So we have our voltage where our little journey starts is 0 at infinity, and it will be negative 76,500 volts at the origin. The work done to move a charge is equal to its change in potential energy. So work is a change in potential energy. And what's potential energy? Well, that's Q delta V, very handy equation. And it just comes from the definition of potential energy and voltage, right? Because potential energy divided by Q is equal to voltage. So delta U is Q delta V. So work done is Q delta V. So VF minus V0, well, VF is this negative 76,500, and the potential out here at infinity, let's put infinity out here, and we're bringing him in over there. Multiply them together, and notice we use the positive for the charge because it's a positive 10 nanocoulombs, and nanocoulombs to coulombs, multiply it by 10 to the minus 9th, and we get negative work being done. Now, why is it negative? Well, let's think for a second. Here's our positive charge out of infinity. If we don't push it, what's going to happen to it? Well, I have two negative charges here, right? It's going to attract it. So it's going to want to go to this point here where you have a negative voltage. So if you want it to move at a constant velocity, I need an equal and opposite force. So I'm actually holding this guy back a bit. All right, trying to balance it off so he moves with a constant speed until he winds up here. So his motion is to the left. And you know what? Let me just erase that because I've got too many arrows there. The charge's motion is this way. I'm exerting a force this way, so I'm doing negative work on that charge. And that's exactly what the answer comes out to be.